fast and deep, energy efficient neuromorphic learning with first spike times. I'll get to each of those words and why they're the title in a second. But first, I want to say that this is work that I started during my master thesis and continued since with my co-first author, Laura Griener. And yes, so we at this conference, we've heard quite a few times that there's some kind of lack of algorithms to train spiking neural networks. And those statements were always accompanied with another statement, which meant that which said that there's a lot of progress in this area. And I'm going to talk about the progress we've made on this. So I'm going to present one such algorithm to train networks of spiking leaky integrated fire neurons that's robust, that needs only spike times as observables for training. It encodes information in the spike times. We've checked the robustness of this algorithm and it's suitable for neuromorphic hardware. And we've checked this by actually putting it on a neuromorphic platform. And that's the BrainScales 2 platform that you've heard also already at this conference about. We tested this on the MNIST handwritten digit dataset, and I'll say the numbers later again or describe them later again. But just as a heads up, we have like a frame rate of 10,000 frames per second, and still very, very low energy. But yes, how do we get here? First, I want to say how we, there we go, why it's actually difficult to learn in spiking neural networks or networks that spike. For this, I want to remind everyone what leaky integrated fire neuron is. So it has a PSP, a postsynaptic potential after a spike input, an incoming spike that is non-monotonic. So it decreases again. This is due to the leak. That's the name-giving leaky integrated fire, name-giving for the leaky integrated fire neuron. And this non-monotonicity in the postsynaptic potential leads to quite a few difficulties. One is a discontinuity. Here you see two scenarios where in one scenario, that's the top one, the spike times, the incoming spikes are a bit further apart from each other. And this little increase in the distance between those two spikes, input spikes, leads to the output spike, which is shown as the arrow on top, to disappear. So the spike time of this neuron, which is again where we encode information or want to encode information, would just disappear. There's a discontinuity in the spike time. There's another problem, which is a non-monotonicity in the function of the spike time. Let's just look at a similar example. So we have, again, two inputs. The black one is fixed. And now if we increase the time between the orange and the black one, we increase this, so we increase the distance between them, and then the output spike time gets shifted to later times. But funnily enough, if we decrease the distance, so move the first spike closer to the second one, the same thing happens. So the output spike time also increases and the spike gets shifted to later times. This non-monotonicity is a big problem in the spiking neural networks. And we've tackled this problem by deriving in a closed form solution or an analytical solution for specific cases, the function for the output spike time. So the output spike time, capital T, you don't have to look in detail at those equations, we have analytical formulas for this, for two scenarios. One where we have the times constants being equal, then the postsynaptic potential is an alpha kernel, and with the help of the lambda W function, this capital W there, we can solve this. And also another case for a factor of 2 between the two time constants, we have a quadratic equation that we can solve. Having this analytic formula for the spike time allows us to derive this formula. You see this on the right. Again, the details are not that important. The big thing is that we have derivatives for those spike times. And this means that we can show, or we can calculate how much an incoming weight or an incoming spike, both of those are responsible for an output spike time, and especially how we need to change the incoming weight or the incoming spike time to change the output spike time. And this allows us to do to solve the quadratic assignment problem exactly, and thus to do, based on gradient descent, error backpropagation in networks of spiking neurons. We've applied this to hierarchical networks of leaky integrated fire neurons that feature time-to-first spike encoding. So we have the saliency of a feature, so for example, the blackness of a pixel is encoded by the time of the spike. An earlier spike encodes a stronger feature. The same thing happens for the label spikes, the decoding of the label spikes. The first spike determines the classification. Now, our algorithm on such a network leads to moving of the spike times or changing the weights in such that the spike times get shifted around so that samples get classified correctly. So this means the network tries to have correct spikes of the classes at early spike time. So you see the top row, the red class at the beginning before training. You can't see any difference between the spike times or the membrane curves, but after training, the red neuron spikes at the very beginning. We've introduced for this a new dataset, the YinYang Dataset. This is a very small dataset that is very suitable for neuromorphic hardware. It features a large gap in the accuracy between what a nonlinear classifier and a deep network can achieve. And this allowed us to train the spiky neural network in detail and to observe how it actually to study the mechanisms of this network. And the three examples that I just showed you were samples from this YinYang dataset. This is just a very short thing. We can train in simulation this network. And on the right side, you see a spatial representation of the samples, and you see the process misclassifications of the network. This is after training. And you see that the misclassifications happen only close to the borders between classes, but the majority of the samples is classified correctly. On this dataset, we've also looked at the robustness of the algorithm, and we've looked at typical substrate-induced distortions. So for example, finite weights, both finite precision and finite maximum weights, and also imperfect time constants. In the derivation, we needed a very precise ratio of the time constants, but we've shown that for noise that is larger than what we see typically on hardware, we can still classify correctly. I said we put this on the hardware, we put it on the BrainScales 2 system. This is a mixed signal neuromorphic system, and I don't have time to go into detail. There are other people that can do this better as well. The main thing is that that the system has an analog core. This enables fully parallel emulation and has enables runtime that is independent of the network size. That's on the chip. On this system, we did classification or training of networks in the loop method on MNIST digit set, and we have a high test accuracy of nearly 96%. We've seen how long it takes. So we stop the time before we send any data to the chip. We let the network run, and once we have the classifications on the host PC again, we stop the time and we can classify all 10,000 MNIST test samples in less than 1 second. All the while, this chip needs only very little power. And this leads to an average energy consumption of only 16 microjoule per classification. If this number doesn't say you anything, for comparison, a banana has about 90 kilocalories. So our results come down to 20 billion classifications per banana. I already have to come to an end. I showed you our algorithm that is based on an exact derivation of the spike time in neural networks. We've applied this to hierarchical networks of leak integrated fine neurons that have time to first spike encoding. I've showed you an implementation on the BrainScales 2 system that is very energy efficient and very fast as well. I've also quickly hinted at the robustness of the algorithm, and I want to stress that our algorithm is the algorithm combined with the coding and very fast and energy efficient chip. Those all three work together to produce results that are, well, very fast and very energy efficient. This is again work done with Laura Greener, and I want to thank her and this is also my supervisor, Mihai Petrovic. Thanks a lot.